And I see that Anna Fiveash is online with us now. Hi, Anna. I'll give a bit of an introduction. So this is a keynote presentation, and the presenter is Anna Fiveash. And I'll say a bit of background to Anna. With regard to undergraduate training, Anna's background originally in psychology, and she has a degree from the Australian National University. And then she went and did a master's, the Masters of Music, Mind and Technology at University of Jyväskylä in Finland, and then returned to Australia to Macquarie University and did PhD in psychology. She was working with Bill Thompson, who was one of the supervisors. Since then, she's been a postdoctoral researcher. She's been for a while at the Lyon Neuroscience Research Center in France, where she works with Barbara Tillman and others, and also a recent stay at Vanderbilt University in the US. I mean, I've known Anna for quite a few years due to the Australian connection. And one thing that was immediately apparent is just her proactivity in terms of being an advocate for music psychology and now music neuroscience research. And she was a very active member of the Australian Music and Psychology Society, and I think even was responsible for launching and then regularly contributing to a very exciting society newsletter. So for a dinosaur like me, who was at the society from the start, it was really nice to see this vigor and energy come into it. In terms of research expertise, Anna's interests cover the relationship between music and language, with respect to rhythm, syntax, psychological processes like memory and attention. And more recently, she's been working on the role of neural oscillations in processing music and speech, working with rhythmic priming type paradigms, training, and looking at the potential transferring of benefits in areas such as children with developmental language disorders. Last thing I'll mention is that recently Anna won a prestigious award from the Australian Research Council to go to the Marx Institute for Brain Behaviour and Development at Western Sydney University. And the topic of that is music and speech as a window into the predictive brain. So it resonates very much with the topics with which we're discussing today. And the title of Anna's presentation for us today is Music, Rhythm as a Window to Understanding Developmental Speech and Language Disorders, the Processing of Rhythm in Speech and Music, or the Processing Rhythm in Speech and Music Framework. Thank you, Anna.
Thank you so much, Peter. That was an amazing introduction. And thank you so much to all the organizers for having me here. I'm really excited about the talks today. They look amazing. Everyone can see my screen and hear me? It's okay?
I think so.
Perfect. Thank you. Yes, I think Peter's introduced this really, really well. I'll just add in addition that this framework is in collaboration with Barbara Tillman, Nathalie Bedouin, and Reyna Gordon as well. So because we're all on our screens and hiding behind our computers, I just want to show you where I physically am. This is where I am in France, in Lyon, which is absolutely beautiful. So if anyone has a chance to visit, they should. And I'm in the Lyon Neuroscience Research Center, which is what Peter mentioned, and in the auditory cognition and psychoacoustics team, which has a lot of we go from crocodile research to coma research and lots of different things related to auditory cognition. And this is also in collaboration with Vanderbilt Music Cognition Lab as well. And like Peter said, I will now be moving to Australia at the end of this year to work at the Marx Institute for Brain and Behaviour and Development. And Peter already said all this, so I just go quickly, but I will be looking for a PhD student as well for the start of 2023. So if this kind of resonates with anyone, we'll be looking at music and speech, perception production, musicians, non-musicians, EEG, behavioral, kind of everything. So this is also in collaboration with Peter as well. But today I would like to talk to you about our new framework, the Processing Rhythm in Speech and Music Framework, PRISM, and how we can use this framework to hopefully kind of push forward research looking at shared mechanisms and implications for developmental speech and language disorders. So just kind of to begin, we have two main aims with putting forward this framework. So we want to inform both fundamental and applied research. So in terms of fundamental research, we really want to kind of investigate the neural mechanisms underlying rhythm processing, and also how these might differ or be impaired across different developmental language disorders. In terms of applied research, we also want to kind of think about how we can investigate how music rhythm training in particular can support speech rhythm and language processing in normal and impaired populations as well. So this is kind of the idea to put forward a framework to help direct some research into this area. There's already some nice research coming out, and it would be really nice to discuss afterwards as well. I know there's a few projects in like kind of happening now. So. But just before I go into that, I'd like to kind of say what I mean by rhythm in music and speech and how they might be related or not related. So if you look at music, you can see this nice simple melody here. So you've got the notes, the different notes. You've also got the waveform up here where you can see the onset of each note. And when we talk about rhythm, this is a big debate, of course, but typically a nice, simple definition is just that it's the temporal patterns created by the onsets and durations of acoustic events in an incoming sequence. So you can see here in blue, you've got the slightly longer notes, in purple, the slightly shorter notes. So you can have this kind of basic acoustic level, but of course there's also this emergent beat level, which is where you might want to tap along, clap your hands. So I'm putting this here with the X's, and I'm going to try to sing this to you. So I'm sorry if there's anyone with a perfect pitch, because I don't think it will be perfectly pitched. But if you have a melody like this, I'm going to click where the beat is. So do 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 do. So I hope this works with the sound. But you've also got higher levels of metrical structure, which is what creates this hierarchical structure in rhythm as well. So in one hand, I'm going to tap the meter with the strong, the 3 X's here, which just means it's like a stronger event. It's more important within the musical piece. And then you've got the slightly weaker, but also strong events as well. So do 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 do. So it works like this. You've got hierarchical structure in musical rhythm. However, you also have a similar thing in speech. So if you've got a basic sentence like this, Aunt Amelia remodeled her living room. You've also got where stressed syllables, where you place emphasis, and you've got the different syllables which are giving Aunt Amelia remodeled her living room. But you've also got the higher hierarchical level as well. Aunt Amelia remodeled her living room, like this. So this is how we're kind of thinking of one way of comparing rhythm in music and speech. So in terms of the similarities, you've got a lot of similar acoustic cues, and the brain is kind of processing them in different but similar ways as well. So you've got your duration, which is your timing, your frequency, which relates to the pitch of the sound, your amplitude or intensity, which gives you the loudness of the music or utterance, and also the timbre, so the instrument or the voice quality. So what I was talking about is with the hierarchical structure, this is a very important part of this. So you've got your hierarchical structure in terms of rhythm, but you also have a hierarchical structure in terms of syntax as well. And based on these structures and the different kind of patternings of rhythm in here, you can create really strong top-down cognitive predictions of what is upcoming. But of course, there's also some important differences which we should always take into account. Quite clearly, music is a lot more regular. It's a lot easier to predict the upcoming note. Whereas in terms of speech, we talk more about patterns of prominence, grouping, and lexical stress. So we have these kind of stressed syllables where we try to direct attention to these stressed syllables. And it's been shown that rhythm in speech is actually very helpful for prediction of these stressed syllables, which often contain more information. And of course, the individual elements, the notes versus words, are different as well. But that being said, it's kind of really interesting to think about whether there are shared underlying neural and cognitive mechanisms for processing rhythm in music and speech. And maybe we can consider using this really nice regularity in the music to then help the processing of the less regular speech signal. So I'm just going to show you first our framework so you have an idea, and then I'll go into the different elements. So we're proposing that there are 3 common underlying mechanisms for music and speech rhythm processing, which we observe across lots of different theories. So the idea is if you have an acoustic stimulus, excuse me, that is somewhat regular, you need precise auditory processing to process the signal. There's also going to be synchronization and entrainment of your neural oscillations to the external stimulus. And this is hierarchical, like we were talking about. And also sensorimotor coupling is very important. So the link between the sensory and motor cortices. I'm going to go into detail of these as well, but just to say there's really important connections between the 3 as well. So you can't just look at one kind of isolated. You have to kind of look at the bigger picture as well. So in terms of precise auditory processing, this is just the ability to discriminate very small deviations or changes in timing, pitch, and timbre. So in speech, it might be something like ba, pa, ka. It's very, very small, 20 to 40 milliseconds of change here. And also in music, differences between very small micro timing deviations or pitch deviations. And this is very important in terms of accurate perception and production as well. There's also the synchronization or entrainment of neural oscillations. There's a big debate here about what is entrainment as well. I'm not going to go into that, but just to say what we're talking about here is really the entrainment of endogenous neural oscillations that are already in the brain, not a steady state evoked potential of just an acoustic response. So this is what you would call entrainment in the narrow sense in terms of the Oblesser and Kaiser paper. So this is kind of just how we kind of track auditory rhythms. And a lot of research is suggesting that this is likely to underlie the perception of music and speech. And the important thing here is that this happens kind of in a hierarchical way. So you've got coupled neural oscillators in the brain, which are tracking different hierarchical levels. And this is what really helps us with prediction as well. Now, sensorimotor coupling is also really important. This is the connection between sensory and motor cortices. There's a lot of research on this as well, looking at if you're just listening to music or speech, we actually see activation in speech, in auditory areas and in motor areas. When you're listening just to music or speech, you see activation in motor areas. So there's this really strong connection, and it's also related to prediction as well. So I just want to say there's a lot of hypotheses which have gone into these, and a lot of different theories which are kind of taking 1 or 2 elements or looking at music or speech or something more specific. So I'm just going to go through a few of those. These have all really contributed to our thinking based on this. And I want to first talk about the opera hypothesis by Annie Patel, which has really laid a lot of the foundation for the more rhythmic studies. So the opera hypothesis is the idea that music training can benefit the neural encoding of speech if these certain conditions are met. So you've got overlap. So you need to have similar neural areas which are processing both signals. Precision, so the idea that music requires more precise, here they're talking more about pitch, but is also related to rhythm as well. More precise timing and pitch than speech. Music training also is very important for it arouses positive emotion. It requires a lot of repetition and focused attention. So the idea is that all of these things can then relate back to helping transfer with this neuroplasticity in the speech system as well. So this is really looking at precise auditory processing more specifically, but this is a more general theory. So I just wanted to put this up because this has really given a lot of background to the other more rhythm related theories. So there's a nice one called the precise auditory timing hypothesis. And this is really looking at the link between auditory motor entrainment and phonological skills. So they're saying, Cheney and Krause are saying that entrainment to music fulfills all of these requirements. So there's overlap in the brain, precision, emotion, repetition, attention, and this underlying plasticity mechanism is what's behind this transfer training from music to speech. So this is looking at more precise auditory processing and sensorimotor coupling. They mention that the entrainment of neural oscillations might be an important thing here as well, but they don't go into detail here. Then I want to talk about the STEP hypothesis by Fuji and Wan. So this is the idea, this is a rhythm-specific extension of opera, and the idea that music rhythm training can help speech and language rehabilitation because the processing of the sound envelope of music is very, very precise. And also when we're synchronizing and entraining to the rhythmic pulse, this is also requiring a lot of, or the different levels of opera, but also a very precise processing as well. And they link this into how this could help other disorders as well. So Parkinson's disease, stuttering, aphasia, and autism, which is really nice. And they look into kind of the more neural brain areas, which are responsible for this as well. So they're looking more at precise auditory processing and sensorimotor coupling as well. They don't mention the entrainment of neural oscillations, but it seems to be the underlying kind of mechanism behind synchronizing and entraining. There's also the temporal sampling framework from Usha Goswami, which is really looking at dyslexia and how people with dyslexia might have trouble following the speech signal in terms of the entrainment of their neural oscillations. So this is a graph from Goswami 2018. You can see here the speech envelope. And the idea is that our neural oscillations in the brain are tracking this envelope also at different levels of the hierarchy. And what's been found through a lot of research is that people with dyslexia often have trouble with this onset. This is a syllable here, and they have trouble tracking this kind of rise time for the different syllables. So this is really related to the synchronization and entrainment. And this is really important and interesting in terms of dyslexia and also extending perhaps to developmental language disorder. So we'll talk about that a bit later too. This is also linked to precise auditory processing, of course, because if you're not synchronizing effectively, you're also having trouble with the precise processing. There's also some sensorimotor theories. So the action simulation for auditory prediction, which is a beat-based model looking really at musical beat, which is the idea that our motor regions receive input from the auditory cortex. They use this input for motor planning, and then they send timing predictions based on this motor planning back to the auditory cortex. And active sensing as well. I'm just showing you these other ones that are really interesting, which is the idea that neural oscillations are generated by the motor system, and then they influence predictive timing and coding. And this is in terms of attention as well as we're amplifying sensory input arriving at predicted times. So these are really looking at sensorimotor coupling, also the entrainment of neural oscillations, but more also for communication between brain regions. There's also a lot of other theories, which I won't go into for timing reasons, but there's also the nice subcortico-cortical framework of speech perception and production by Kotz and Schwartz, dynamic attending theory as well in terms of entrainment of neural oscillations and attention, and also predictive coding. So these are all the kind of things we've tried to put together and try to make a larger framework with the idea to have a parsimonious kind of connection between all of these different mechanisms, which could be underlying music and speech rhythm processing. So now I want to go into some evidence for timing deficits in developmental disorders. So how can this, what we know about rhythm in music and speech and their overlap, how can this then help people who have developmental language disorders? So in the paper, we talk about dyslexia, developmental language disorder, and stuttering. And the reason we really focused on these was that all of them had speech and language as a primary deficit. They all show high prevalence in the population with persistence into adulthood. They all have communication difficulties that exert a personal and professional toll. And interestingly, they all have links with deficits in timing. So just really quickly, definitions. So dyslexia is associated with learning difficulties for reading and spelling, and it's usually associated with phonological processing deficits in the perceptual domain. Developmental language disorder used to be called specific language impairment. So there's been a bit of a change in terminology relatively recently. But this is the delayed and disordered acquisition of morphosyntax, so grammar and vocabulary, with impaired oral language acquisition as well. So this can be expressive, so in production, but also expressive receptive. And stuttering is just a difficulty producing fluent speech. So people who stutter might prolong their syllables or produce speech with irregular temporal patterns, but they generally have intact acquisition of vocabulary, grammar, and reading. And across all of these disorders, these deficits cannot be contributed to other factors like low IQ or neurological damage, inadequate learning environments, or hearing impairment. So what is the evidence here? So there's been, especially for dyslexia and developmental language disorder, there is evidence for impaired rise time and stress perception and impaired temporal sampling of the speech envelope. And this has really been led by this temporal sampling framework, looking at dyslexia and DLD specifically. More research on dyslexia for now. They also tend to show general impairments in synchronization to an external beat. So if you're tapping along to something, typically people with dyslexia and DLD particularly, but also stuttering, have trouble compared to control groups in synchronizing to an external beat. So there might be some kind of timing impairment here as well. In terms of more music type studies, there's impairments shown across various rhythm, perception, production, and synchronization tasks. So this is really interesting. So if we're finding these timing deficits in both speech processing and music processing, this is kind of also part of the theory and how we can really train these networks. So there's been impaired rhythm, perception, and production in dyslexia, DLD, and stuttering. And in stuttering, more specifically, there's also evidence for impaired unpaced tapping. So this is when you're just told to tap at a steady rate, however you want. And one of the kind of theories behind stuttering is that there might be a disruption to internal timing circuits. So perhaps based on the basal ganglia and sending kind of internal timing signals. So this is, for now, I saw some looking at dyslexia as well, but it's a bit difficult also with the children because they're more variable in general. And I want to just mention here as well, we've got another paper presenting the atypical rhythm risk hypothesis, which is the idea that maybe we could start looking at potential atypical rhythm processing very, very young before the language measures can start being used, because this might be a risk factor for developmental speech and language disorders. If you have poor timing as a young person, it doesn't mean that you will get a developmental speech and language disorder, but you might be at more risk. So have a look at that paper if you want to. It's really looking more at the genetic basis of this as well. So going back to the framework, this is again all together, and we have some predictions of the framework as well. So first of all, if we see deficits in one or more of the underlying mechanisms, these should be related to deficits in both speech, language, and music processing. So of course, we have to be a bit careful because there are important connections between the different mechanisms as well. But this is kind of one of the things we want to look at in the future. How can we link these different impairments at a neurological level, perhaps, to the actual behavior? So the second one is that different expressions of speech language difficulties across different disorders should be related to specific impairments in one or more of the underlying mechanisms. So we can look more carefully to see across disorders, is there something common which is coming out here? And how is it related as well? And the third, more on the applied side, is that targeted training of these mechanisms specifically should be able to enhance related skills in both music and speech language processing. So I'm going to go into these a little bit in more detail, but these are the predictions we're putting forward for now. And I am talking about these 3 disorders, but there's also been timing deficits shown across autism, attention deficit hyperactivity disorder, and developmental coordination disorder as well. I would say there's a bit less research at the moment, and it's sometimes a bit conflicting. So it's really good to be able to start looking more carefully across different disorders as well. So what we're kind of proposing in the applied side of this framework is that we could really benefit from using music rhythm training as a complement to speech therapy. So of course, we're not saying to replace speech therapy. It's just this idea that music rhythm is a bit different, but if it's training the same underlying mechanisms, then it could be a really nice way to complement speech therapy and make this a more broad training. So we would predict that if you're training more directly the 3 mechanisms, so precise auditory processing, you could have people discriminating small timing differences, make it into a game, something like this. Have people synchronize and entrain to the hierarchical structure at multiple levels. So tap along or synchronize with different beats, for example, and change between the 2 even. Sensorimotor coupling, really you could have rhythmic production tasks with auditory feedback, or just playing in a group as well is giving this strong connection as well. And what is really nice is that beat and meter perception in terms of rhythmic training is particularly valuable because it seems to tap into these 3 mechanisms more broadly. So at a kind of starting level, we could look more closely at music rhythm training, and then we could get more precise. So the additional elements as well of music rhythm is that, or music training in general, is that you've also got all these extra benefits. So like in the opera hypothesis, it helps with focused attention, emotion, but also motor functions, moving. It's also the social aspects. It's enjoyable, it's motivating, and it's cost effective and easily administered as well. So there's a lot of really good reasons to look more closely at music training and music rhythm training in general, and more specifically. So I want to talk a little bit about music training in both the short and the long term. So we can kind of think about using both. In terms of long-term training, a lot of this research has been done in people with dyslexia. There's also a lot of research outside of the developmental disorders, but I want to focus here on this. So there's a nice randomized control trial with Flagnacho et al. In 2015, where they looked at children with dyslexia from 8 to 11 years of age. So they had 24 in a music group and 22 in a painting control group. And the music training really focused on the rhythm and temporal processing, which is really nice. And they found increases in both groups, of course, because over time, children get better. But they also found that the music group outperformed the painting group in various measures of reading and phonological awareness, which is really nice. So this is a really nice kind of controlled study. And one of the things with this kind of research, there's also some other studies here that I want to just put up. So Frey et al. For voice onset time, enhanced voice onset time perception. Thompson et al. For phonological awareness, and Bonacina for reading as well. So have a look at those if you're interested. But one of the things with these kinds of studies is that it's really, really important to have random assignment and an active control group. And there's a bit of a discussion in the literature at the moment around this. Random assignment is important because children who elect to participate in music classes are probably already more motivated to do so. So that's an kind of important factor. And having an active control group is also really nice. So this painting works really well, or like sports training I've seen as well. Because just the idea of being in a group and having attention, it gives a lot of extra factors. So just to make sure that it really is based on the music training, this is really important. And the type of musical training is important too. So there's a lot of studies looking at more broad music training, which is great because we're seeing influences here, but we don't really know what part of that training is influencing the language outcome. So here we're kind of suggesting music rhythm training might be a really valuable way to kind of focus in, but it's a bit tricky, I know, to run these big, long studies with different training types. So it's just interesting to start thinking about kind of the best combinations of training here. In terms of more short-term training, we've been working a lot on rhythmic priming, and these findings that people are getting that rhythmic priming can enhance grammaticality processing just in the short term. So this has been found with children with DLD and with dyslexia. And it's just this idea that if you hear this regular rhythm, I'm going to play you a sound. Here we go. Okay, so if you hear a regular rhythm compared to something like this, an irregular rhythm, the idea is that your neural oscillations start to entrain to the predictable regularity in the regular rhythm, but they can't do that for the irregular rhythm, right? So we do this for 30 seconds to give time for the brain to really kind of globally entrain. Then we start to present sentences. So we stop the rhythm because the idea is that these are endogenous oscillations. They're not stopping immediately. They should sustain after the rhythm has stopped. And then we present speech. And we do this, typically we have about 6 short, naturally spoken sentences, and people judge if they're correct or incorrect. So typically when we do this, grammaticality judgment is increased after the regular rhythms compared to the irregular rhythms. And it's nice that this is also working in DLD and dyslexia as well. So this could be a kind of a short-term idea to help with this. And this is really based on this synchronization entrainment of neural oscillation. So if we're providing this kind of regularity, precision within the rhythm, this could then carry on to the less regular speech signal. And I just want to show you really, really quickly, we've got a really exciting study kind of in the works right now, where we're looking at a developmental language disorder. So this is a big project in France with French children and in the US with American children to see if we can extend this rhythmic priming paradigm to other types of tasks. So this is working with Reyna and Eniku Ladani in Nashville, and a lot of a really great team here as well. So for now, in France, we have collected 19 DLD children and 19 TD, typically developing children. And we have tested them on 3 different rhythmic priming tasks. So we have a sentence reproduction task and also a relative clause picture matching task and the grammaticality judgment too. We've also got some control tasks and a lot of measures of their language abilities, short-term memory, IQ, a lot of different things. So I just wanted to bring this up now that this is kind of in the works. We have preliminary analyses going on, which look really exciting. So hopefully we can present this to you next time. I just want to also say rhythmic cueing, so this short-term rhythmic cueing or auditory stimulation also really is helpful for people who stutter. And singing in particular enhances fluency in speech for people who stutter, but also in aphasia, for example, like with melodic intonation therapy, if you're singing the words, often people with aphasia who have production deficits are really able to say these words. So there's also short-term ideas which could be very useful. So one thing that's important is how are we going to measure potential deficits across these 3 mechanisms? So in terms of precise auditory processing, we can see in the brain directly if there is impaired or reduced neural responses to fine-grained or precise auditory information, like this. And I will say that this has mainly been done in dyslexia so far. So these studies are all from dyslexia, but people have found atypical rise time perception neurally, deficits in pre-attentive processing of vowel onset time and syllable duration, reduced speech encoding at these lower level frequencies here as well, and more general auditory processing deficits as well. So this will be really interesting to look more closely at this and try to figure out what is a great way of measuring this across different disorders as well. In terms of the synchronization and entrainment, we can really, there's a lot of nice techniques now to look at how our brain is aligning with the signal, with the speech signal, with the music signal. So we can look at reduced or abnormal phase alignment and connectivity of our neural oscillations to the external stimuli. And we can look at this hierarchically as well. So this has also mainly been done in dyslexia. There's some evidence that people with dyslexia have impaired or abnormal phase alignment as well. And in terms of sensorimotor coupling, we can look at the connectivity between auditory and motor regions. And this has been shown, especially in stuttering, that there is reduced connectivity between these two areas. So these are kind of ways that we can think about investigating this question, and then also ways that we could measure the effect of music rhythm training. So we could have these measurements beforehand, the rhythm training, but maybe focusing on 1 or 2 or 3 of the mechanisms, and then measure again to see if we can improve these mechanisms, mechanistic processing, but then also if that would transfer to the speech processing as well. So I just want to give you also a broader kind of context and outlook, cognitive and biological. So what we've looked at today is pretty much the neural and cognitive side, which is what we're really interested in. And we've also looked a little bit about atypical or disordered speech or language processing. So I think it's really important to do a bit of a focus on developmental speech and language disorders. And if we can use this framework as a bit of a guide to start looking more broadly at timing deficits across different disorders. And I know a lot of people are starting to do this, so this is really exciting. There's also an important genetic aspect here, which is talked about more in the atypical rhythm risk hypothesis paper. I know that there'll be a presentation later today on the new MAPLE framework as well, which is really nice and looks at the genetic side as well. So I'm looking forward to that. We also are thinking about how we can do different rhythmic training studies, treatment, how we can kind of use kind of individual-based approaches as well as the group level to kind of figure out the best way to come at these questions and try to improve speech and language processing this way. There's also a lot of really important individual differences and differences across development, within disorders, across disorders. And Elvira had a nice presentation about this. Even intrinsic motivation and reward can change how this works. So it's really important to kind of have a targeted treatment approach as well to try to figure out how this is working and how it can best help the most amount of people. So just going forward, there is a need for really well-designed studies with large sample sizes. So because these kind of studies take quite a long time to set up, to run, to analyze everything, if we can really have a strong idea of what will hopefully work, this would be really nice. And with the large samples, we can look at these individual differences as well. So I think this is going to be a really important thing going forward, the individual differences. Maybe we can kind of consider the different constellations of deficits that might come out, even across disorders, but also within disorders, because I think like for example, maybe people with dyslexia and DLD, they might have specific problems with the neural entrainment of the oscillations, which is also then affecting the precise auditory processing. But maybe it's reversed as well, we don't know. But maybe they're fine with the sensorimotor coupling. But then on the reverse side, you might have people who stutter, who are really having a problem with their sensorimotor coupling. But then in terms of neural entrainment or precise auditory processing, maybe they don't show any deficits. And then even there's a lot of different types of problems within one type of disorder, which is kind of grouped together. So if we can kind of figure out a way of testing individually these mechanisms, we can see what really needs training. So this is the idea. And it would be really nice I know it takes a lot of participants is the only problem, but it would be really, really nice to kind of check this across large samples. One of the other problems with this kind of research is that everyone's doing different rhythmic training, everyone's having different outcome measures. Even in language, it's quite different, and in music as well. So it's often hard to figure this, to compare across big studies. So maybe if kind of we could all agree somehow as a field, what would be the most kind of interesting battery to look at, for example, based on pilot testing and things like this, or previous research as well. Maybe we could start doing kind of bigger studies using the same measures, so we can kind of really compare across groups. And this will be really interesting. It's a bit, yeah, I think we need to kind of talk about this as a collective as well. So I'd be really interested in hearing your thoughts on this as well. And if we can focus our rhythmic training programs on these three mechanisms, I think it would be really valuable. I think at the beginning, we probably need to look more broadly at rhythm training, but then within that, we can start to kind of focus on the mechanism. So this is really a discussion to be had, and we're kind of putting forward this framework with the idea that people who are in the position to run these kinds of studies will be able to think about this and kind of communicate across various fields as well. One thing that's really interesting is that when we talk about rhythm, it's not just a stable construct, right? You have lots of different rhythm skills and rhythmic competencies. And one of the interesting things with this is that if some groups of researchers are using a rhythm-based memory task, for example, if you have the same different task, we've actually got some recent research suggesting that is a different competency to kind of tapping along to a rhythm, or different, like the beat alignment task, if you're saying if a triangle sound is on the beat or off the beat. So actually there's kind of distinctions even in these kinds of tasks. So one thing that we really need to also think about is if we find in one study, the dyslexics don't have problems with rhythm perception, but they're looking at the memory side of rhythm perception. Perhaps they do have trouble with synchronization in the production side or even in the alignment side, but maybe they can use other cognitive mechanisms such as their memory, which isn't affected, to do well on these tests. So this is kind of something we need to think about. We have a new paper coming out really soon, I hope, looking at different rhythmic competencies as well, and what different tasks might be valuable. So the goal of all of this is to have kind of, in the long run, right, the goal for patient-centered kind of precision medicine approaches that really can be informed by neuroscience. So I'm really interested to see your opinions about this. Feel free to email me as well at the end. Because this would be really great if we can kind of come together and make this really a valuable contribution. So just in terms of a bit of a wrapping up everything, we have our three mechanisms here. We really wanted to provide a framework where we can kind of have parallel research at both the fundamental and applied levels. And these can have some communication between them as well. We want to kind of see what's happening in the brain with timing, with people with different types of developmental language disorders, and see whether this timing deficits we're finding can be seen across many different disorders, or if they're more specific, or maybe more specific to different types of mechanisms within the disorders as well. So the aim is really to uncover these underlying impairments. It'll be really great to keep investigating this. There's a lot of new research coming out on developmental coordination disorder, ADHD as well, and autism. So it's really nice. But there might also be different types of timing impairments, which we need to investigate. It's exciting. And the goal in the long term is to really be able to train these specific impairments. So if we can find these underlying mechanisms that are affected in both music and speech, especially in terms of rhythm, it could be really nice to complement the speech therapy approaches as well, to have just a different way of training the same underlying mechanisms. It's also really important to take into account these individual differences. Also, the connection between the mechanisms is really important here. So with that, I would like to thank my collaborators on this project, Barbara Tillman and Nathalie Bedouin in Lyon, and Reyna Gordon in Nashville in the US. And thank you also to all the funding agencies which have supported us on this journey. So thank you very much.
Thank you very much, Anna.
No worries.
Really a brilliant, expansive overview of the topic. And a few questions have come up in the chat in YouTube. I'm not sure if you're looking at that. I can also put them in the chat here in Zoom so that you can see. The first one from Sonia Simon. So the question I'm quoting now, Anna, since timing capacities are highly variable in childhood/development, where do you place the threshold between typical and atypical timing capacities as a precursor of cognitive function?
That's a really nice question. I mean, it's really important to compare to control groups. This is kind of, sorry, I'm seeing myself double right now, so I'm just going to take off the YouTube. It's really important to kind of look at age-matched controls here, I think, because yes, exactly. When you're very young, there's a lot of studies that have tried to do kind of unpaced tapping or something like this, and the children are just very variable. It's really hard to find this. So the idea would be to see if there is a difference between typically developing children, children at this age. Oh wait, yes. So if you want to look at a threshold, I guess we need a lot of research on this to figure out where this threshold might be. And what is typical in these populations at this age and what is atypical. So basically this would kind of be my answer. I think we need more research on this. There's also some more points in the atypical rhythm risk hypothesis paper as well, which is more this idea here as well.
And you can see in the chat there's another question from Dwani Sadafal. Does PRISM predict enhanced language processing with musical training in individuals who don't suffer from language or timing impairments? And then a follow-up. If so, would you propose similar mechanisms that lead to such gains in both groups?
Yeah, thank you. That's a really nice question. Definitely. I think it's the same mechanisms that we are looking at. So I really focused on the developmental language disorders here because it's more kind of necessary, I guess. So typically developing children typically don't have so many problems with speech processing. But even this would really be an advocate for music training at a young age across the population, right? Because I think these really important links between music and speech in terms of rhythm, but also across different areas, can really help language processing. So the idea of kind of keeping music education as a really important facet of general education, I think is very important. And I would say, yes, that the mechanisms are similar in these groups. And this is there's a lot of what I didn't show here is that there is a lot of correlational studies as well, looking at connections between musical aptitude, musical training, and rhythm processing skills, but also speech processing skills. So because they're correlational, it's a bit hard to know for sure if this is a causal relationship, but there is a lot of research on typically developing children and adults that there are really important connections here. So yes, PRISM would predict enhanced language processing with musical training. So everyone should be, I think I'm talking to an audience who would probably agree with me here, but musical training I think is very important. Yeah.
Okay, next question is from Christina Lubinus. In the rhythmic priming task, did you find the beneficial effect of the rhythmic prime for different prime rates? Or put differently, did you vary the frequency of the prime?
Thank you for this question. We've really been trying to figure this out. So for now, I don't think I mentioned, but our rhythmic primes are at 2 hertz. So 500 millisecond beat rate, like this. And then our sentences are naturally spoken. So the idea is that the accented syllable rate in the sentences is approximately 2 hertz. And the kind of syllable rate is around 4 to 5 hertz, like would be typically found. We were really interested in this question. If we change the frequency rate of the prime, but we keep the speech the same, do we see really the 2 hertz benefit, or is it just benefiting across everything? We've actually tried this a number of times without amazing success. So I'll tell you what we've done. Our first one was we checked this regular rhythmic prime compared to a fast rhythmic prime. So we sped up the speed of the rhythm to, I think it was 1.67 hertz rather than 2 hertz. So it wasn't that much faster because we didn't want it to sound crazy, but it was significantly faster. And we found no difference between those two conditions in children. And then we weren't sure then if that was because both of them were helping or if there was just no difference. So then we've run a new study looking at, we did this in adults too, but it didn't work either. It was the same. And then we did a new study looking at the regular rhythms, the fast rhythms, but also slow rhythms. And we added irregular rhythms. So we've done this now in 20 children. I think we need some more power actually, but there's some pandemic issues. But visually, the irregular rhythms are reduced compared to the 3 regular, fast or slow rhythms. This isn't significant for now. We've got other measures which I'm currently looking at. We've got the beat alignment test in these kids as well, and some other things like reading age. So there's kind of more to come on this. But basically, for now, it seems that the prime rate isn't really affecting the speech signal, but this could also be because these rhythms are complex and they have multiple levels within them, and the speech signal is also naturally spoken, and so there's a lot of fluctuations in that as well. So that's my long answer, but not for now.
Yes, you're getting a good workout with these questions, Anna. The next one is from Ria Sano. So there's 3, it's broken into 3 parts. Neural oscillation was also suggested to be a candidate mechanism for syntactic processing. As prosodic, morphosyntactic, and phrasal syntactic boundaries differ, I'm wondering how entrainment of neural oscillation can be a candidate mechanism for both prosodic and syntactic processing. Do you have any thought about it? And do you predict that atypical entrainment of neural oscillation leads to both prosodic and syntactic processing deficits?
That's a brilliant question. And so my PhD was actually about syntactic processing, which it's really interesting to put all of this together. So for now, we're really focusing on rhythm, but I mean, I definitely think that neural oscillations are important for the kind of the syntactic side as well. And there's a lot of research kind of by the David Popel group and Giraud and everything, looking at the different levels that are being tracked. So kind of the syllable level, the phrasal level, the larger levels. But I think that's really interesting also for syntactic processing, because usually the more important words, I'm talking about speech now, but usually the more, it works for music as well, the more important elements are also on the accented, in the accented points in time. So I would say there's a very important kind of connection between the prosodic, morphosyntactic, and phrasal boundaries. So this is the nice question. So how can entrainment of the neural oscillations be a candidate mechanism for both? And I think what is happening here is that you've got this kind of rhythmic regularity in your speech, which is allowing for the entrainment of our neural oscillations. But this is actually, I mean, the thing that is rhythmic in speech is the content, right? This is what's coming across. So I think there's a very important connection there. So what we're entraining to should technically be the more important structural elements of these music or speech signals as well. So just making out, sure, I've got everything. Do you predict that atypical entrainment leads to both prosodic and syntactic processing? That's really nice, and that's important for DLD as well, developmental language disorder, because they often have trouble with syntactic processing. And this is especially evident in the kind of relative clauses where you have the boy who gave the girl, like when you switch around the subject and object, and it's hard, it's not a linear order. People with DLD have a lot of trouble with these sentences. So I think there's a few things happening. I think it's important in terms of the hierarchical structure, both of the rhythm and of the content. So yeah, I think we need to look into this more. And I read your recent paper, which was looking at this, which really nicely as well. And it'd be really nice to talk about that more as well, and how to connect these, because we really are looking at rhythm specifically here, but I think it's very much connected because the rhythm is giving us the syntax, basically.
Right, and we come to the final question from Music Cognition. The talk focused on speech with musical rhythm as a tool to treat disorders. What about the other way around? Could speech rhythm also improve music disorders? Are you planning studies on this?
I love this question because I've always wanted to look the other way around as well. The problem that I see is that most people are speech experts. So it's actually quite difficult to kind of improve this. But I would say that, yeah, if you could, but how would you train speech rhythm? This is kind of my question, because it's not so regular, the speech signal. So the nice thing about music is that it's really regular, it's really predictable. We can use this enhanced precision to then go to the speech signal, which is less regular. But if we're kind of going the other way around, I'm not sure how you would train the speech rhythm processing specifically. I mean, I guess you have people who go to kind of elocution schools, or the presenting people on the news or something, and they I guess they would be experts in speech rhythm. They're really controlled in the way they present news, things like this. Maybe we could look about them. If they're experts in speech rhythm processing, then maybe it could help. But I'm just not sure about how to turn it around for now. I think the interesting point for this is the precision and the regularity in the music rhythm, which can then go to speech. So currently not planning any studies around this. It would be super interesting. So if anyone has an idea of how to do that, it would be great.
Okay, so that's it. Thank you very much, Anna. There's a lot of applause, and there's even a heavy metal type Devil's Horns accolade there, and a stamp of approval. So let's end it there. Thank you again, Anna. I just want to leave a bit of time for people to get a tea, or for those in Bavaria, a schnapps, before we continue with the next presentation.
Thank you.